Okay, BC Unit 1, Assignment 7, Office Hours. Check your answers if you haven't yet. Pause the video if you need to. Right now, pause it. I'm going to move it. Pause it if you need to. That's it. That's the whole worksheet. So go ahead and do some of these. I think your best bet on these ones is to sketch each of these graphs. See if you can do it from memory. Then you should be able to answer any of these questions from a simple sketch. 20 is kind of like parametrics. We did it the other day on the worksheet, but you don't even need to think of it as parametrics. These are problems you can do without a calculator. So let's go. Okay, so first ones are just trig equations without a calculator. I guess we're just going to do degrees, reference angle, when to sine equal 1/2, that first angle 30 degrees, when is a positive quadrant 1 and 2. So x equals 30 degrees plus 360k, and x equals 180 minus alpha 150 plus 360 degrees k. So the answers from 0 to 360 are just going to be 30 and 150. So this is the kind of work I would show. When does cosine, ignore the 1/2, ignore the negative. When does cosine equal root 3 over 2? It's that first angle, 30 degrees. What quadrants is negative? 2 and 3. So x equals, quadrant 2 would be 180 minus alpha 150 plus 360k. Quadrant 3 would be 180 plus alpha 210 plus 360k. So the answers between 0 and 360 are just going to be 150 and 210 degrees. We should write the degree symbols. Otherwise, no symbol by default means radians. Okay, when does sine equal, ignore the whole 2x thing. When does sine equal root 3 over 2? Positive, ignore the negative. That's at 30, 45, 60 degrees. When's it negative? Quadrant 3 and quadrant 4. So 2x equals, quadrant 3 be 180 plus alpha 240 plus 360k. And quadrant 4 is going to be 360 minus alpha 300 plus 360k. Now we deal with the 2 on the inside. It's going to cut the period in half, which means we should have double the answers. So x equals 120 plus 180k. And x equals 150 plus 180k. And x equals 120, 300, 150, 330. So you guys should be pretty good at solving equations. Factor sine x, 2 sine x minus 1. Set this equal to 0. Set this equal to 0 and solve, which is essentially using inverse trig, because right here, to get rid of the sine, you would take inverse sine on both sides. So we're doing inverse sine, but just kind of in our head, say, well, when does sine equal 1/2? 30 degrees. When is it positive? Quadrant 1, quadrant 2. When sine equal to 0? 0 plus 180k. X equals, quadrant 1 would be 30 plus 360k. And quadrant 2 is going to be 180 minus alpha 150 plus 360k. So x equals 0, 30, 150, 180. Don't forget about 360. Okay. Number 5 is a trig inequality. So we're going to do all the same work, but then we're going to do a line check. So we're going to factor out a cosine 2x. 2 cosine 2x left over inside, minus 1. So cosine 2x equals 0. And cosine 2x equals positive 1/2. Alpha is, well, it goes 1, root 3 over 2, root 2 over 2, 1/2. So 0, 30, 45, 60. Quadrants 1 and 4 is where it's positive. Cosine equals 0 at 90 plus 180k. We're going to divide by 2, divide by 2. We're going to get x equals 45 plus 90k. Here, 2x, quadrant 1 is going to be 60 plus 360k. And quadrant 4 is going to be 2x equals 360 minus alpha 300 plus 360k. So then we're going to divide by 2, x equals 30 plus 180k. Divide by 2, x equals 150 plus 180k. So x equals 45, 135, 225, 315, 30, 210, 150, and 330. So then we're going to do a line check. We're going to go 0, which doesn't have a dot. These are all going to be solid dots. So in order, 30 degrees, 45 degrees. See, 135 degrees, 50 degrees, 210, 225, 315, and 330. We're going to close it at 360. So you're going to test a value. Tell me what you're testing. I like to test 0 whenever possible, which I can do because it's not a root. Cosine 0 is 1. 2 minus 1 is 1. Is not less than 0 is false. True, false, true, false, true, false, true, false. So your answer, interval notation, will be bracket 30 degrees to 45 degrees. Union bracket 135 degrees to 150 degrees. Bracket union 210 degrees to 225 degrees. Bracket union bracket 315 degrees to 330 degrees. There you go. So that's all just kind of a bunch of review. Now here's some new stuff, but this is kind of like what we've been doing. Because we're saying, all right, what's alpha? When does sine equal root 3 over 2? 60 degrees. What quadrants? Is it positive? Quadrant 1 and quadrant 2. Now these are inverse to begin with, so you are at the mercy of principal values, which always include unit 1. So this is for sure 60 degrees. Or in radians, that would be pi over 6, pi over 4, pi over 3. So I'll probably ask you for both on your next test. When does cosine equal 1/2? Well, 30, 45, 60 degrees. Pi over 6, pi over 4, pi over 3 radians. What quadrants is negative? Quadrant 2 and quadrant 3. But principal values are never quadrant 3 for any of these. It's got to be something touching quadrant 1. Quadrant 3 doesn't touch quadrant 1. Quadrant 4 touches quadrant 1. Backwards. So our answer is going to be 180 minus alpha 120 degrees, or pi minus pi over 3, which is 2 pi over 3. 8. When does tangent equal 1? Well, better question is, when does sine over cosine equal 1? Well, it's when both of these are the same. So what angle alpha does sine and cosine give you the same value? 45 degrees. What quadrants is it going to turn out to be positive? Quadrant 1 because they're both positive. Quadrant 3 because they're both negative. But principal values is never quadrant 3. Always includes quadrant 1. So your answer is 45 degrees pi over 4. Okay, when does sine equal -1? Well, that's at 270 degrees, or 3 pi over 2. When does cosine equal negative root 3? Well, alpha equals 30 degrees, pi over 6, reference angle. We're going to be in quadrants 2 and 3, but it's inverse cosine, so never quadrant 3. Quadrant 2, it's going to be 150 degrees, 5 pi over 6. When does tangent equal root 3 over 1? Well, that's more like when does sine over cosine equal root 3 over 1? Sine over cosine. So what's the reference angle? They should both have the same thing. That's going to be 60 degrees, pi over 3. What quadrants could we be in? Well, it's either quadrant 2 because sine's positive, cosine's negative, or quadrant 4 because sine's positive, cosine's negative. So this negative belongs to either one of them. Now, principal values say that we're always using one of the quadrants touching quadrant 1. So this one's a little less obvious. So you can think back to that graph, and it was like this. It was quadrant 1 and it was quadrant 4. So it's not going to be quadrant 2. So it's going to be, now you got to be careful. You got to go backwards into quadrant 4. So it's not 300 degrees, 5 pi over 3. It's negative 60 degrees, negative pi over 3. Got to go in quadrant 4 backwards. All right. Next one, if you draw a picture here, you can think, okay, well, this is adjacent over hypotenuse, and adjacent has to be positive. So that's either here or here. This is when adjacent is positive. Hypotenuse is 5 for both of these. So it's either quadrant 1 or quadrant 4, and it's always quadrant 1 for inverse trig. And then we want to take sine of that same angle. So we don't know what the angle is, but we have, we could find the opposite side. I'm going to call it y. So it's going to be x squared plus, 2 squared for the x plus y squared equals 5 squared. So y squared equals 25 minus 4 is 21 squared of both sides, plus or minus. The minus would be the one down here, and the plus would be the one right here. So we want the positive one, so it's going to be positive square root of 21 over the hypotenuse. There you go. Same idea here. We're trying to find theta. This is opposite over hypotenuse. So a little picture would help opposite. Now, hypotenuse has to be positive, so for sure the negative belongs to opposite. So it's got to be down for sure. This is where you get a negative opposite side. Hypotenuse is 3. Now, so it's either quadrant 3 or it's quadrant 4, but this is inverse trig, so it's never quadrant 3. It's for sure this. That's your angle. So now you could do tangent is opposite over adjacent. So we got to find the adjacent side. So we do x squared plus negative 2 squared equals 3 squared. So x squared equals 9 minus 4 is 5. Square root of both sides, plus or minus. We're going with the plus because this is positive square root of 5, whereas this one over here would be negative square root of 5 in quadrant 3. But we ruled that out. So opposite over adjacent would be negative 2 over the square root of 5, or negative 2 root 5 over 5. There you go, little inverse trig. Consider the graphs. Which of the graphs are always increasing, symmetric to the origin, 1 to 1, have a limit that goes to infinity, have inflection points to the origin, have an inflection point on the y-axis. So multiple answers can exist here. Now, I think having a quick sketch of each of these graphs would help. So I'm going to graph inverse sine. Now, inverse sine comes from the cosine curve being flipped across y equals x. So it kind of looks like this sideways. And we just take this part right here, right? So we're just taking that part. Cosine, similar idea. Cosine starts here. And when you flip it across y equals x, 0, 1 becomes 1, 0. pi over 2, 0 becomes 0, pi over 2. And the graph looks like that. Oh, we just take this portion of it. So inverse cosine looks like this. Inverse trig looks like that. I'm going to flip it. So inverse tangent is like that. And then the negative of inverse sine is just going to be that graph upside down. And the negative of inverse cosine is going to be that graph upside down. And the inverse of negative tangent is going to be that graph upside down. So which of these are increasing? A is, C is, E is. A, C, E. Which ones have symmetry by the origin? Take one half, fold it, and fold it again. A does, B doesn't, C does, D does, E does not, F does. So I'm just looking at these graphs. Okay, which ones are 1-to-1? So that means they pass the vertical line test and a horizontal line test. All of them. A, B, C, D, E, F. Which ones, as you take the limit to infinity, go to infinity? None of them. None of them blow up. Which ones have inflection points at the origin? A does, B does not, C does, D does, E does not, F does. Which ones have an inflection point on the y-axis? Well, all the ones that have inflection points at the origin, that is on the y-axis, but also B does now, and E does, so all of them. A, B, C, D, E, F. So that's how I do it. Draw some sketches. Now for a little parametrics without even necessarily knowing parametrics. So you have x is a function of t, y is a function of t. So dx dt is greater than or equal to 0. Well, let's find dx dt. It's derivative of x with respect to time. So that's going to be 2 cosine t, and we want to know, was it greater than 0? So that's the same thing as cosine t greater than 0. Well, what are the roots? We could do a whole line check here. When does cosine t equal 0? So when t equals pi over 2 plus pi k. So for us, since we're doing 0 to 10, which is a little more than 3 pi, it's going to be pi over 2, 3 pi over 2, 5 pi over 2. Pi is about 3, so that's 15 over 2 is 7. 7 pi over 2 would be like 21 divided by 2 is more than 10. So those are your roots. So then we could do a line check. 0 to 10. These are open dots. Pi over 2, 3 pi over 2, 5 pi over 2. Test the value. X equals 0. Because no 0, that's true. False, true, false. So our answer is 0 to pi over 2, bracket, parenthesis, union, 3 pi over 2 to 5 pi over 2. There you go. There's just a bracket on the 0 because it cuts it off right in the middle of a true statement. So that's part A. Part B says, well, let's find dy dt, which is going to be negative sine t, and set it less than 0. So that's the same thing as sine t is greater than 0. T equals 0 plus pi k. So t equals 0, pi, 2 pi, 3 pi is about 9 point something. 4 pi would be beyond it. So then we do a line check, 0 to 10. These are open dots. Open dot 0, open dot pi, 2 pi, 3 pi, test a value, tell me what you're testing, x equals pi over 2, sine's 1, which is true, true, false, false, true, false. So the answer is 0 to pi, union, 2 pi to 3 pi. Now, if these were uglier numbers, then we could use graphing calculator, graph it, and use the graph to help us. So there you go. That's it.